Have you ever found yourself just staring at a pile of data, knowing there are interesting groups hidden inside, but you just don't have any labels to guide you? Well, today we're going to pull back the curtain on a really powerful and I think super intuitive technique that does exactly that. It's called hierarchical clustering. We're going to build this thing from the ground up so you can see not just how it works, but how it helps you find those hidden stories within your own datasets.
So here's our game plan. We'll start with a big picture of clustering. Then we'll dive right into how the hierarchical method actually works. We'll get into the nitty-gritty of distance and linkage, the core mechanics, and then we'll learn how to read its signature visualization, the dendrogram. After that, we'll see the algorithm in action and wrap it all up with some practical tips to get you started.
All right, first up, let's get the lay of the land. Before we can start building these cool hierarchies, we really need to understand what clustering is all about and where it fits into the grand scheme of machine learning. So this is it. This is the fundamental question that gets us started. I mean, imagine you've got a mountain of customer data, or thousands of news articles, maybe even a bunch of genetic information. You have this hunch, right? A feeling that there are natural groups in there. You know, the big spenders, the articles all about sports, the genes that seem to act alike, but you don't have any pre-existing labels. How on earth do you find those groups?
Well, this is exactly where the big split between supervised and unsupervised learning becomes so important. Now, with supervised learning, like classification, the algorithm gets to learn from data that already has the answers. It's got an answer key. But with clustering, we're playing in the unsupervised sandbox. There is no answer key. The whole point isn't to predict a label that we already know, but to discover the labels themselves by finding the structure that's just naturally sitting there in the data. And believe me, this is not just some abstract academic concept. Clustering is happening all around us. Retailers use it to slice up their customer base for targeted marketing. Search engines use it to group news articles together by topic so you see related stories. Biologists use it to find patterns in gene expression. It is an incredibly powerful tool for bringing a little bit of order to messy, unlabeled data. Okay, so we know we want to find groups, but how does the hierarchical approach actually do it? And what makes it so different from other methods you might have heard of, like k-means? The secret sauce is right here in the definition. See, hierarchical clustering doesn't just hand you one set of groups. It builds a full family tree of possibilities, a whole hierarchy, starting from individual data points all the way up to one giant cluster, containing everything. And the biggest advantage? You don't have to guess the number of clusters, that infamous K, before you start. The structure it reveals actually helps you decide. Now, there are two main ways to build this hierarchy. The most common one is agglomerative, which is bottom-up. Think of it like people at a party. Everybody shows up as an individual. Then people start forming pairs. Those pairs merge into small groups. Those groups get bigger, and so on, until the whole party is just one big cluster. The other way is divisive or top-down, and it's the exact opposite. You start with the entire company in one giant cluster, and then you keep splitting it into smaller and smaller departments. For our purposes, we're going to focus on the agglomerative approach because, honestly, it's what you'll use 99% of the time. So if we're going around merging the closest clusters, that kind of begs a question, right? How do we actually define closest? This brings us to the two absolute core mechanics of this algorithm: how we measure the distance between points, and then how we measure the distance between entire clusters. First things first, we need a way to measure the distance between any two individual data points. The one we all know from school is Euclidean distance, the straight line as the crow flies. It's the most common choice, but there are others. Manhattan distance is what you'd use if you could only move along a grid, like walking city blocks. And cosine similarity is amazing for text data, where you care more about the direction of the data than its size. This choice right here is the very first decision that will shape your final results. Okay, so that's points, but how do we measure the distance between whole groups of points? This is where linkage criteria come in. Single linkage is kind of like the optimist. It defines the distance between two clusters by looking at their two closest members. It's like saying two friend groups are close because the two best friends, one from each group, are really close. The thing is, this can sometimes lead to what's called a chaining effect, where clusters get stretched out and start looking more like a snake than a nice tight ball. On the flip side, you have complete linkage, which is more of a pessimist. It defines the distance between two clusters by looking at their two farthest members. In our social analogy, this means two groups are only considered close if everybody in one group is pretty close to everybody in the other. This method is great for avoiding that chaining effect, and it's what you want when you're expecting compact, ball-shaped clusters.
Then there's average linkage, which is the democratic choice. It literally calculates the distance between every single possible pair of points across the two clusters, and then just takes the average. It's less sensitive to outliers than the other two, which makes it a really great, balanced, middle-of-the-road approach. And finally, we have Word's method. This one's a little different. At every step, it looks at all the possible merges it could make, and it picks the one that leads to the smallest increase in within-cluster variance. Now, that's just a fancy way of saying it wants to keep the clusters as tight and compact as possible. It's always trying to create the most harmonious new group, which is why it's a super popular default choice. It tends to create really nice, evenly sized clusters. So as the algorithm is doing all of this merging, step by step, it's actually building a history, a story of how the data is connected. And this whole story gets captured in one beautiful and incredibly useful visualization, the dendrogram. The dendrogram is, for all intents and purposes, the family tree of your data. At the very bottom, it shows every single data point as a leaf. And then it shows you exactly how and when those leaves were merged into branches, and how those branches eventually grew into the main trunk. The vertical axis is absolutely key here. It represents the distance. The higher up on the chart a merge happens, the more different those two clusters were when they were joined. Now, reading a dendrogram is a skill, but I promise it's straightforward. You start at the bottom with all your individual points. As you move your eyes up, whenever you see a horizontal line connecting two vertical lines, that's a merge. And here is the most powerful part. If you want to pick a certain number of clusters, you just cut the tree with an imaginary horizontal line. The number of vertical lines your cut crosses, that's the number of clusters you get. A good tip is to look for the longest vertical lines that don't have any merges. They often suggest the most natural place to cut. All right, we've got all the pieces now. Distance, linkage, and our visualization, the dendrogram. Let's put them all together and walk through the step-by-step process of the agglomerative algorithm. This right here is the engine of the whole thing. You start by treating every single data point as its own tiny little cluster. Then you calculate the distances between all of them. You find the closest pair, based on your linkage rule, whether it's single, complete, or wards, and you merge them. Boom. Now you have one fewer cluster, you update your distances to this new merge cluster, and you just repeat the process over and over and over until everything has been merged into one giant supercluster. And you know, the best part is that modern libraries like scikit-learn and Python make this almost ridiculously simple. With just a few lines of code, all that logic we just talked about comes to life. So here, we're initializing the model, and we're telling it two key things we just learned. First, n clusters equals 3. That's us telling the model where we want to cut that dendrogram to get 3 final groups. Second, linkage equals ward. That's us picking our specific rule for merging. Then we just fit it to our data, and all those steps we discussed are executed in the background. It's pretty amazing. Okay, so the theory is great, but what about when the rubber meets the road? Let's wrap this up with some super important tips and common pitfalls to make sure your clustering actually makes sense in the real world. Okay, this is absolutely crucial. First, you have to scale your data. If one of your features is, say, income in the thousands and another is age from 20 to 80, the income feature will completely dominate any distance calculation and your results will be meaningless. Also, if you have tons of features, you might want to consider using something like PCA to reduce the dimensionality first. And, last but not least, be mindful of the cost. Calculating all those pairwise distances takes time and memory, so for really, really big data sets, this method can get pretty slow. So if you're going to take anything away from this, let it be this checklist. First, your choices of distance and linkage are everything. They will define your results. Second, use the dendrogram. It's not just a pretty picture, it is your main analytical tool for understanding the structure. Third, always validate your results. Sure, you can use a metric like the silhouette score to get a number, but just as important is using your own expertise. Do these groups actually make sense? And I'll say it one last time for the people in the back, remember to scale your data. At the end of the day, hierarchical clustering doesn't just spit out an answer. It gives you a map of the relationships hidden deep inside your data. It really invites you to explore, to cut that tree at different levels, and to discover the natural groupings that have been there all along. So, what story will your dendrogram tell?